The most important skills that we're going to be talking about is actually one of the focuses today and a little bit tomorrow is on data acquisition. How do I get the data? In our class, the virtual machine is going to play a role in that because we're going to look at how you acquire data from sources like SQL databases, from Mongo databases, from web scraping, from files, over SSH commands where you're executing commands and trying to process that output as the input into your machine learning or data science project. So that's the role that the VM plays. Sorry, I don't know why my watch gets all excited sometimes when I talk. So that's really the role that the VM plays. It's not where the labs are, it's just where some of the data is that we're going to load. All right, so then let's actually jump in. Let's start talking about some of our material. I said to you that our labs are going to be using this tool called Jupyter Lab. Now, you may or may not have heard or have run across this before. We have a little picture of it down there at the bottom. Jupyter Lab is known probably best for being used for interactive Python development. In fact, it's sort of based on IPython or interactive Python. And what it provides for us is a web interface, though, as some of you might know, they just recently released a desktop version of this. So in other words, it's effectively got everything all in one place, and I don't need a separate web browser to interface with it. I'm going to recommend you not use that this week. It is both too new, and I have already found there are some weirdnesses in how it functions. So please, for this week, use the labs as we've written them. We'll be using it through a web browser. It doesn't really matter which web browser you use. It works the same way on all of them. But please use the Jupyter as we have designed it in the class this week. So it's known most for being able to write and interact with Python scripts interactively, primarily by being able to write code into individual cells and execute it and see how it functions. Now, really, that whole notebook can be viewed as a single script. And in fact, you can download it or export it as a single script. But it allows me to tinker with bits of the script, maybe change a variable value and then rerun another cell. So it's as though I'm taking a Python script and doing an autopsy on it and being able to test and tinker with individual pieces as I go. It proves to be a wonderful place to experiment with Python, and particularly with the kinds of problems we're going to be working with. But it is not limited to working with Python. In fact, Jupyter supports a whole bunch of other languages through these things called kernels. So a Jupyter kernel is just, you can think of it as a library that supports a thing you can do, like the R language, the C language, Fortran, Ruby, Scala, Haskell, in addition to SQL shells and Mongo shells and a whole bunch of things. You can really implement any kind of interactive shell you'd like to within Jupyter. We're going to be focusing on using it with Python. In fact, that brings us to the language of choice this week. We do have people from time to time who take this class who already have some data science credential. I've actually found that kind of interesting, and having polled the people who take this class who have taken, say, formal machine learning classes or formal data science degree, and inquiring why they're taking this, it's most often coming back to that same thing that I was saying to you. How do I take the information I have and translate that into a problem I can solve? Particularly, how do I do it with information technology or information security data and turn that into a thing I can do? Well, I bring this up and the idea of people with data science credentials because folks in that space are likely much more familiar with R or with MATLAB. We do not use those two tools in this class, or those languages in this class. Instead, we're using Python. We're using Python for a few reasons. R is a domain-specific language in the statistics and data science field for manipulating data. And it has a whole bunch of support for statistical and probability and other kinds of functions. It is an excellent tool for data science. But if I want to get my R project to interface with my web API or to interface with my SOAP protocol or SOA architecture inside of my enterprise, or to do almost anything else, that is going to be very challenging because R is really only designed to be used for mathematics, statistics, and data science. Python, on the other hand, is a general purpose programming language that happens to have libraries that can be used for statistics and mathematics, most especially NumPy, which we'll be making heavy use of. The advantage of this is that I can write my machine learning code or my data science code using Python, and I can get that Python to interface with, say, my enterprise architecture or with my web API, or to serve things directly as a web interface, because it's a general purpose programming language. Even more than that, though, Python is very widely used in information security. Not only is it a rapidly increasing in popularity language, but within our space, we have transitioned from, say, a decade and a half ago, where everything compiled was written in C and everything else was written in Perl or Ruby. Python was a beginner then, to Python dominates our space. This is the primary language that's used in IT and in information security. The only language that is of similar emphasis, especially in the IT world generally, is JavaScript. I really would not want to do this work in JavaScript, but that language is also pretty predominant in the information technology field, not so much in the machine learning or data science field. So that's why we're going to be using Python. We've also made a very clear decision on which machine learning framework to use. And the one we're going to be using is TensorFlow. Now, there actually are a couple of others. Very few of them are worth mentioning because there has been a big die-off within this space. There have emerged two real leaders in this space, TensorFlow and PyTorch. I should just mention that there was a recent survey done of data scientists who make use of Kaggle. Now, I don't know if you've heard of Kaggle. Kaggle is it's a website you can go out to. They run all kinds of AI, machine learning, data science-y kinds of competitions. People post questions out there. You can find some limited data out there. It's an interesting site. I personally find that there's very, very little useful material there. But if I'm, for instance, trying to find a sample data set for something, I might just cruise through there to see if there's something out there. But I don't find it particularly useful. In any event, they did a recent survey, and yes, that is the site right there, Kaggle. So with that survey, they found that scikit-learn had way more of a following than either TensorFlow or PyTorch. So if you happen to look at that survey, I just want to clarify. Scikit-learn is not a machine learning library from the point of view of what we're going to talk about later in the week. Because where we're really heading is into using machine learning and AI, which, sure, there is machine learning we're going to do before that, but I'm really focused on deep learning networks, creating the artificial networks that try to mimic how we think. That's really where we're heading. And scikit-learn really doesn't do that. What it does do are things like decision trees and random forests and support vector machines and a whole bunch of other things that are forms of machine learning, but it really is not the cutting edge of what's happening today. On the other hand, things like random forest, PyTorch and TensorFlow don't do those things. Those tools are designed for multi-level perceptrons, for deep learning neural networks, for convolutional networks, and is how we're going to use them. So when I'm saying that these are the predominant tools, I'm talking from that point of view. From the point of view of deep learning neural networks, TensorFlow does continue to lead the pack. So we're choosing the market leader, not because it was created by Google, and we're not choosing to not use PyTorch because it is supported and funded by Facebook, or should I call it Meta now. So that's not why we're not using it. But instead, you're going to find that PyTorch is predominantly used in academia, but rarely used in commercial products for machine learning. TensorFlow seems to be rarely used in academia, but is widely used in commercial applications. I think I know why. The reason why TensorFlow, at least in my opinion, is so dominant in the commercial space is that they have very wide support into many different languages. So if you'd like to create something for your iPad that uses a deep learning neural network, you can do that easily because it interfaces directly with Swift. They provide the libraries for that. Or if I want to do it for something on my Windows platform, I can interface it into C# code very easily. I want to do something with my website. They provide a JavaScript library to be able to install a model there. PyTorch has been trying to catch up with that, but TensorFlow does continue to lead. And I think that that's going to generally remain true. I do find that people will claim that PyTorch is much easier. I don't think that's true. I think that PyTorch is much easier if you have always used PyTorch, because I do find PyTorch is a little bit weird to use. On the other hand, of course, with any library, it's going to take some time to learn how to use the library. But I think you'll find that the way we use TensorFlow is very easy to use. More on that much later. We don't get to those tools until around Wednesday. I did mention this NumPy tool to you. So NumPy is a numeric processing library for Python. It's a high-speed numeric library. We're going to be spending a lot of time with this, and I find that for people who have a strong Python background, NumPy is the thing that's going to be most different for you, because you're going to look at what we do with NumPy, and you're going to feel like, actually, you know what you'll feel like? You will feel like I feel when I go to the Netherlands, because I took several years of German when I was in college, and my German, please don't test me out. So that's more than 30 years ago that I took German, and I don't have much occasion to speak German. I used to work for a company that had an office in Munich, so I was there from time to time, but my German is very rusty. Even so, when I go to the Netherlands, I hear people speaking, and I feel like I should understand what they're saying, but I don't. And NumPy is going to be a bit like that. It's almost like it's a dialect of Python, because you're going to look and say, oh, I know what that is, and then see what it does and say, well, that's weird. That's totally not what I would expect, because it is Python-based or uses Python, but some of the ways you use it aren't going to match the way you use arrays and lists in Python. So just be on the lookout for that if you're already a Python pro. The reason we're using it is that it provides a really fast way to do the computations. Python is our primary tool. Python is not a fast tool. It doesn't matter why. We're not going to get into that. But NumPy provides a bolt-on high-speed numeric processing library that's compiled into native code. It also allows us to work with linear algebra operations very efficiently, which is going to prove to be very important. More on that later. We're also going to make heavy use of Matplotlib. Now, there are a whole variety of visualization and plotting tools that you can use from Python. One of the ones that's very popular is called Seaborn. We're not going to use Seaborn directly in class. Instead, we're using Matplotlib. But why are we using Matplotlib? Well, it turns out that pretty much every plotting library we use these days, certainly from Python, but even in other spaces, if you go back again 20 years, GNUplot or GNUplot, that was what most people used. But Matplotlib has really taken that space. Matplotlib is the underlying library that's used by Dash, by Seaborn, by most everything that produces any kind of graph that you're looking at. So we're not going to use the higher level libraries. We're going to use Matplotlib. And I'm choosing to do that because it's quick and dirty. The way we're using these is to see, visually, hey, how did that training go? Let me just look at that real quick. I can do that very quickly with Matplotlib. And everything that we do in Matplotlib can be transferred directly to any higher level library that you choose to use. That means that rather than using Seaborn and then let's imagine that your organization is using some other library, so you have to now learn that other library. If we spend the time learning Matplotlib, you can transfer that knowledge directly to any library that's built on top of it. So Matplotlib is where we're going to be going. We're also going to be making some use of a tool called Pandas. Now, I find that this is another tool that people will come to the class with some experience with, and it is a very powerful library for manipulating data. We will use Pandas occasionally in this class and to do a few specific things, but not to do a lot. And this is a conscious choice. I've had students ask about this, and I want to explain. I'm not focused on Pandas so much. It turns out that most of the things that we do using NumPy, we could accomplish using Pandas. Sometimes we could accomplish them more easily. But I'm not focused on Pandas for a few reasons. With Pandas, you are going to run into issues sometimes with very large data sets where Pandas simply can't handle it. You're going to have to go get some other tool to use it, to handle the data. With large data, I can actually build, I don't want to get too far ahead, but I can build some solutions using NumPy to handle the big data more easily than I can with Pandas. But there's another huge reason. NumPy supports n-dimensional arrays. N-dimensional meaning any number of dimensions. You pick it. 1-dimensional, 2, 15, 100-dimensional, just doesn't matter. NumPy can handle it. It's a generalized tool for dealing with n-dimensional arrays. Pandas is not. Pandas is built on top of NumPy, and Pandas handles 1 or 2-dimensional arrays, and that's it. So that means that when we start dealing with problems that have maybe 3 or more dimensions, Pandas just isn't useful. Or let me say it a different way. To use Pandas requires a lot more effort to make the data look like something I can deal with in Pandas. And that really shouldn't be the focus. The focus should be directly on manipulating the data, not on manipulating your tool to be able to manipulate your data. So I'm actively choosing to use NumPy predominantly in the class. And I believe that that actually has a payoff because since it is the underlying library for Pandas, and since the structures that we're using within NumPy are so similar, they are analogous to the things that are happening inside of TensorFlow. So much so that we can think of the things in TensorFlow as NumPy arrays, even though they're not. NumPy is a better tool for us to focus on. So that's why I'm doing that. Pandas is definitely worth some time. You will see it play a part from time to time this week, and we're going to look at some ways to use it. But NumPy is the real focus. We also are going to spend some time with SQL. Now, I mentioned this to you previously. I said this is one of the reasons the VM exists. And you might be wondering, why are we covering SQL? Is that, I signed up for machine learning and applied data science. What does that have to do with anything? One of the most important tasks that you do in this space is acquire data. Someone who is working on machine learning or data science style solutions, data-driven solutions, should be self-sufficient when it comes to acquiring and manipulating the data. For this reason, we're going to cover a couple of data type technologies that you should be able to interact with. SQL is just one of them. We're also going to spend time talking about document stores. In fact, we're going to use Mongo as the case study for this. But what we're going to be talking about really does transfer to other kinds of document stores as well. What I wanted to do is make sure we talked about SQL. We'll be using Postgres for that for our study. Though, of course, what we talk about will apply to any kind of SQL database you have. Just the mechanics of what you have to do will change. And in fact, for those of you who have some SQL experience, I've chosen Postgres here rather than something like Maria, because Maria is actually much simpler to use. I actually prefer using Maria in most of my projects. And that may make you say, well, wait, then why did you use Postgres? I chose Postgres because Postgres is much more widely used as an enterprise solution, or if you're not using open source, it is much closer to what you will experience using something like Oracle or using an IBM solution. Maria is not. Yeah, it runs SQL, but how the database is managed is very different than what you do in other enterprise solutions. Postgres is much closer, and that's going to matter in our data exploration section. So you'll see that when we get to it. In a similar way, we could have talked about Couch or any of a variety of different document stores, but I've chosen to use Mongo in this case because it is the thing I most often see people using for quickly built solutions that are coming out of agile web application development. And in that space, since we do want to store things in some kind of a database, Mongo is the thing that is kind of the go-to. And we'll see why that is as we go. And we're going to dig into some of the details, even the things that are listed here, and how it's stored in the back end and how you do the queries and what the advantage is of one versus the other. So we will be talking about that as well. But we're going to be using Mongo as our example. There's some stuff that we're not going to be covering, at least not beyond what's here in these introductory slides. You're going to run across the term big data, which people do like to throw around. I actually had a funny experience in London about 2-3 years ago, where during the 503 class, just out of curiosity, let me just here. So some things I know I'm going to ask you, so I've pre-typed these polls, but some I don't know. Have you taken Sec 503 before? So just out of curiosity, if you don't mind there, just pop a quick poll in there. Have you taken 503 before? I don't know how many of you folks I've met before. So for those of you who have, I had a gentleman in London who took 503, and 503 is deep packet analysis and network threat detection and that kind of stuff. That's what that class is. I think it's a phenomenal class, but I'm a little bit biased. You took it with Mike. Excellent. So I had a gentleman sit through that class, and almost everything we said, he's like, well, I could do that with my data lake. Data lake is a big data term. He has an IBM data lake. A data lake is a thing that you just shove all of your data into, and we'll talk more about that in a few minutes, but it's really about the storing of data. That's what big data is about. How can I store the data? More importantly, store the data without loss. That's the real goal. Store everything without loss. But there's no focus really on how I get insights out of that. That's not the focus of a data lake. It's the storage and putting it into a format where you could interrogate it and perhaps do some transformations on it to gain some insights from that data. So it was so funny because everything we said, he's like, well, I could do that with my data lake. And finally, we did call him out on that much later in the week. And it turned out that he couldn't do that with his data lake, because a data lake is something you could put everything into. But for example, there is no way you are taking every packet that passes over your network and putting a copy of it into your data lake. You just don't do that. No one does that. So people throw around data lake and big data, and they don't often know what it is or know how to use it. This is really about storing the data efficiently so we can get everything or get the things out of it that we need to. One of the ways that we get things out of it, I really like that, Nathaniel. One of the ways that we get things out of it is using an approach called MapReduce. Now, there's a lot of other ways we do transformations on data in a data lake, but this one's worth mentioning because while we're not going to be doing big data, of course, everything we talk about here can be applied using data coming out of some big data solution. MapReduce is a technique we use to do that, and actually is something we use under the hood in some of our solutions. MapReduce is actually a joining of two different terms. The idea is I want to apply some transformation to everything in my data set. That's called a mapping function. I want to apply this function to everything in my data set. And then I want to aggregate those results. That's the reduction. That's the reduce. And the example that's usually given, I actually like the example, it's a good one, is that of maybe trying to figure out how many times a word appears in a corpus of text. That's actually a problem we're going to deal with. So I want you to imagine that we have some huge corpus of text. Maybe this is coming out of Project Gutenberg, and let's say we have 100 million books. And what I want to know is, I want to create some natural language processing kind of solution. And in order to do that, one of the things I want is how frequently does each word appear in that entire body of text? So what words are there? How frequently do they occur? Well, how could we do that? I could write a piece of code. So we have 100 million files. Every one, there's a whole, 100 million files in here. And what I could do is write some code that is going to iteratively take a file, count the words, and after it counts the words in that file, it's going to go and get a different file. How long will this take? Well, it's going to take the time that it takes to read 100 million files sequentially. That is a solvable problem, but that is a slow solution. It's a very direct solution, but very slow. MapReduce seeks to parallelize this problem. I still need to read 100 million files, but do I need to process them sequentially? So what if doing that, what if instead of doing that, what if I say, let's create a whole bunch, I'm just going to use circles here, let's create a whole bunch of processes that are going to, each of which will read a set of files. So maybe I create 1 million processes. Each one of them will read 100 files and count the words in those files. So I have 1 million processes, and I now have the count of words in each book sitting in each one of those. I have mapped the problem. I have gone through and applied this function to every one of them. I've transferred it from a book to a count of words. But now I want to know, what is the aggregate? What's the total? Well, I have 1 million of these. So once again, should I take a single thing, a single machine, and have every one of these create a connection to it and push their results? That's 1 million connections. That's not going to be good. Should I go the other way? Should I have this machine reach out to 1 million different hosts? That is also not ideal. That is very time consuming. So what if instead, what if we do a little bit more divide and conquer? What if I create, so we're at 1 million hosts, what if I created 100,000 hosts? And what these 100,000 hosts do is each one of them is going to interrogate some set of hosts to get or to aggregate down its count of words. And then from there, we aggregate down to a smaller set. And so on, until we're down to just that single node. What we're doing is massive parallelization. On the one hand, we're parallelizing vertically. We're having a lot of different machines do the map problem. And then the aggregation, where again, but now scaling horizontally, where we have lots of things within each slowly aggregating down until we have the final solution show up here. A map-reduced solution is something that we'll frequently use cloud resources to do. And of course, the cloud providers love us to do this because every one of these instances is costing us money while it's running. But the advantage is, or what we're doing is trading computing time to processor intensity or number of units involved. I'm spreading this problem over in this case, millions of systems. And by doing that, I'm able to solve the problem very quickly at a much higher short-term computing cost. I'm actually adding to the computing cost because I'm doing the aggregation multiple times, but it ends up taking less time overall, rather than doing the brute force approach. So that's what the map reduce idea is. It's about parallelizing the problem in order to make it or solve it more efficiently. We're not going to do any large-scale map reduce things, but I'm pointing that out to you because we will absolutely see that approach happening inside of some of the solutions that we work on. This brings us then to just a general understanding of what data means. And from the point of view of data science, data probably doesn't mean what you're used to it meaning. Because in the field of data science, we're really borrowing from the field of information. In information theory, data isn't data as we typically use it. Because in information technology, we manipulate data all the time. We use that word actually interchangeably with information, but they are not the same thing. Data is just raw fact. It has no structure, and there is no direct information or interpretation or context. I sort of think of it, or to me, it's analogous to a Zen approach to data. If you step on something that feels a little squishy and round, you might immediately jump to a conclusion that you're stepping on a snake. Now, where did I get that? Well, have you ever had your hand laying somewhere, or maybe you were moving and brushing your hand against something, and with no rational explanation, you get some sensation on your hand, something brushes your hand, and the thought that flashes through your mind is, there's a spider on my hand, or some insect, and you react, you just jerk your hand. And have you ever had that happen? So you have gone from something brushing your hand to spider, but there's no context to get you there. And of course, I'm sure you've had it happen where you have that reaction, and it wasn't a spider. A leaf brushed your hand, or something else, something brushed your hand, and it wasn't what you thought it was. We tend to jump directly to the interpretation of something without actually looking at all the facts. So what we're saying here is, well, rather than saying that's a snake, we're instead going to just look at the data that's available, the facts that we have. This is round, it's long, it's green, it has scales, and it's moving. Now, you might take all of those things together and say, that means snake, but the data itself are just those facts. When you take that data and you put it all together, that data, so round on its own, that could be anything. That could be a marble. Round and long. Okay, not a marble. That could be a stick. And squishy. All right, not a stick. That could be a garden hose. Has scales. Not a garden hose. So the more context we add to this, it helps us to build information. An analogy that I also like about this is the idea of taking a group of blind men. So this is not mine, of course, I'm sure you've heard this. And you are going to get a group of blind men to describe an elephant to you. They, of course, have never seen an elephant. It's their first experience with an elephant. And one of them, he is handed the tail of the elephant. So how does he describe the elephant? It is long and skinny and round. Another blind man who's touching the trunk says, well, it's long, but I'm not sure how skinny it is. It's much more like a snake. Another one who's touching the ear will describe it as being broad and flat and maybe like a bat. Another one who's touching the leg is going to describe it as like a tree trunk. One who's touching the side is going to describe it as a wall. No one of those things is an elephant, but in the context, all of those things taken together allow us to deduce or produce an elephant from that information. Having that information then leads us to the ability to make a decision. Like, hey, I have just taken these facts and put them together, and I have decided that that is a snake. So I better get my foot off the snake. That's totally fine. And of course, we often make or react to things without having all the data, and it can help to protect our lives. That's great. But when I'm trying to do something with a computer system, I need to view that data and assemble that data in a way as to generate information that can ultimately be used to make decisions. And that is the goal of data science, to take data, manipulate it into context and structure that produces information, and to then use that information to drive decisions in the business. How do we do that? Well, the way we do it, the way we're doing it in this class, the way it's done in data science generally, is to use statistics on it. We're going to spend a fair amount of time tomorrow discussing a variety of statistical tools. There will be both descriptive tools. What's the average value? That's a descriptive tool, in addition to predictive kinds of tools and inferential tools. More on that tomorrow, and actually a bit of that on day 3 as well. We also make use of the field of probability. We'll be discussing that at a very, very cursory level tomorrow. We're not going into it very deeply, but we're going into it enough that we're able to understand and then implement a naive Bayes classification tool. That's both to understand probability and how to build one of those, but we're also going to be comparing that solution to other things we build later on in the class. Another way we do it that is data science adjacent or related, but not every data scientist knows how to do this. Data scientists should definitely be in this space and in this space, but they may not be in the machine learning space. So that's the other way that we are going to take the data, convert it to information, and then hopefully be able to make decisions, is through machine learning. And the real focus of the class, beginning especially on day 3. So then, all right, so okay, I've said most of this. So that means or brings us to some of the steps that we do in data science all of the time. We acquire the data. That is the main focus today. There's a little bit about that tomorrow, and it's something we do the whole week, but the focus of today is on the acquisition of data. That means that today we're going to spend a lot of time pulling that apart, but in the rest of the week, while acquiring the data will be there, we're going to just shoot through that fast. This is an important thing. As we're covering things in this class, while we're writing code, while we're examining code, we're discussing an idea, if there's something that's not clear to you, it is pretty important that you get that cleared up. The best way to do it is to ask a question. For example, let's imagine that I'm talking about NumPy arrays in a little while, and I start talking about how I can slice NumPy arrays, and it's different than Python, and look how we can do it, and look, there we go, and I can reshape them. Great. Let's imagine there's an aspect of that you don't understand. Make sure I explain it in a way you understand it. Ask questions, because that's not going to go away. Once we have discussed doing array slicing with NumPy and reshaping arrays, I am going to assume you know what that means and how that works. So the first time we do it, we'll spend a lot of time on it, but I'm not going to spend a lot of time on it again. So I'm going to assume you know it and just do it in the later labs. Similarly, once we know how to acquire data out of a Mongo database, let's say, we're going to spend a lot of time the first time, but then the rest of the week, we're just going to assume you know how to do that. Make sure you understand things when they're presented, because if you don't, it's going to hurt you later, because you're now going to have trouble with later concepts because you're missing something in the lower end concept. Our focus today is on acquiring the data. We will deal with data generation later in the week. We'll actually do that on Thursday and Friday. We then always need to do some kind of cleaning or pre-processing, some kind of manipulation to get the data into a shape we can use it. We will be doing that every single day, organize the data, and then generate some useful result. This is the process a data scientist works through. You start with some interesting question, like, let's take tomorrow. And this is largely a solved problem, and I get that. But tomorrow, one of our questions will be, is there a way for me to mathematically or algorithmically determine whether or not something is spam? And that problem is interesting because that is it this or that? That problem comes up again and again. Is it spam? Is it a phishing attack? Is this an attack or not? Is this malicious? Is it this or that comes up again and again. So tomorrow, can I determine if it's ham or spam? We'll start with a simple problem. So that's my question. In order to do that then, or to solve that, I need to acquire some data. In our case tomorrow, we're going to be acquiring a whole bunch of email. I need to kind of pre-process that and turn it into a clean format. Do I need mail headers, for instance? Are those of any use to me? Or is it just the body of the email that matters? In looking at the body of the email, do I need to have, say, HTML tags in there for HTML encoded email? Or can I just exclude that stuff? All of that is part of the acquisition process. Next, we explore the data. We try to understand it. We're going to visualize it in different ways, see if we can find relationships within the data. And in fact, I would really tell you that the exploration phase and the apply phase, these are much more of a loop. You can end up getting a false impression in the field of data science and in machine learning, because if you go out and read people's blog articles about things they've done, if you go read magazine articles about what people have done, if you go out and look at research papers that are published on a site like Archive, you're looking at the end result. And the way those are presented, you can walk away feeling like, wow, so I just have to do this and I get an answer. So this is a very easy field, and that's not the case. The solution they came up with, they may have been through 100 different tries of things that didn't work at all. Things that they thought should work, but just don't. Let me give you an example of this. It's something we're not actually going to be covering in the class, but we have a research project going on right now involving some log-based anomaly detection, doing it differently than things we're going to cover in the class, kind of a different approach toward it. And we have been through, we've got one that works pretty well. We expected it to work well. It does work well. We're using a different approach that should absolutely work. We've tried it probably about 50 or 60 ways so far, and it just won't work. That doesn't mean that that's not a valid approach. It means that we just haven't quite gotten to the right mix to get that to work. Now, if we end up publishing a paper on that, do you think we're going to write up the 100 different ways we failed? No, we're going to write up the way we did it that works. So you really should view these two steps again as really iterations. I'm going to explore the data, As I'm exploring it, I'm coming up with ideas of ways that I can kind of apply some technique to get to the result I want, but lots of times that won't work. So we're going to explore some more, try it again, explore some more, try it again, and then eventually, when it works, share some insights. In this space, we say that someone who is a data scientist, they are a blending of statistics and mathematics. We're going to be covering that. Computer science, we're also covering that to a degree. The computer science element of this is that they should be able to write some code. We're going to be using Python in our case. And they should be able to interact with data storage systems. Things like web services and APIs, SQL servers, document stores. So we're going to cover that aspect as well. And they would then also have some field of domain expertise. For us, that domain expertise is information security. And that's the piece that I'm hoping that you're bringing to class. Now we have a variety of different problems we'll look at this week, all from the field of information security. And I'll give, a quick refresher on a little bit of it as we introduce those problems. But I'm really hoping that you're bringing that part with you. That then is going to bring us to the beginning of our first real meaty section. That's just the introduction, which is going to be a refresher on Python. Before we do that, though, it has already been an hour. So I'm going to set a timer here for, let's say 10 minutes for our first break here, and we'll take a short break. Go ahead, get up, stretch, walk around.